Settle in and let your breathing slow, as if the air itself is getting heavier. You are drifting downward through dark water, and the last blue daylight thins into nothing. It feels like silence, but it is really a steady pressure holding you the way a blanket holds your shoulders. Down here, the ocean is not a wilderness. It is a cold storage room for the modern world. Most of the internet does not float in space. It lies on the seafloor, inside long armored cables that look strangely ordinary. And when those cables get scraped, pinched, or quietly broken, nobody sends a hero. They send a patient machine with lights like sleepy eyes and hands that never hurry. Tonight, with the Sleepless Scientist, you get to follow that careful work in the dark. You might think the internet is weightless, like a cloud that lives above you. Wrong. It is mostly a long, physical nerve pressed gently into sand, crossing entire oceans. You are still sinking, and the water around you is getting colder. Not dramatically, just decisively. The light does not switch off, it simply runs out. Sound changes too, because down here, there is no wind and no waves to clap. There is only the soft, constant suggestion of distant motion, carried through water and hull. If you had ears made for this place, you would hear engines as a faraway purr. You would hear your own descent equipment creak like an old staircase, learning patience. And under you, the seafloor comes into view, not as a dramatic cliff, but as a plain, a wide, sleepy desert of silt. It looks empty until your eyes learn what to look for. A cable does not announce itself. It does not glow. It does not hum audibly. It simply lies there, a dark line that is somehow too straight to be natural. Picture a garden hose that is given up on gardens. Picture it armored, heavy, and slightly awkward. This is the soft-spoken backbone of the internet, resting like it has always been here. The cable is not alive, but it behaves like something that wants to survive. It is wrapped in layers, each one meant to deal with a different kind of disappointment. There is plastic to keep seawater from creeping in like gossip. There is steel to handle pulling forces because oceans love to tug on things. There is a copper layer in many designs to carry power for repeaters, the little devices that keep signals strong, and at the center, there is the part that does the real work. Optical fiber, a hair-thin strand of glass, so pure and precise that it can guide light for thousands of miles. You might imagine electricity rushing through metal, like a crowd in a hallway. But here, the messages are light, not the warm, friendly kind of light that makes sunsets. This is disciplined light, injected into glass, reflected inside again and again, never allowed to escape. The trick is something called total internal reflection. In human terms, it means the light keeps bouncing like a tired ping pong ball that cannot find the edge. So your video, your messages, your maps, all of it becomes pulses, tiny flickers that mean yes or no, on or off, in patterns so fast you could never count them. The cable does not care what you are sending. It does not care if it is a love letter or a bank transfer or a poorly considered argument. It carries it with the same indifferent grace. Near the coast, these cables dress for trouble. They get thicker. They gain more armor. Sometimes they are buried under the seabed because humans near shore are busy and careless and equipped with anchors, Fishing nets also have a talent for grabbing what they should not. In shallow water, the hazards are loud, frequent, and expensive. But out here in the deep, the cable can relax a little. There are fewer anchors, fewer nets, fewer people doing impulsive things. The deep ocean is still dangerous, but it is a slower kind of danger. It is landslides that take their time. It is earthquakes that do not make noise, but rearrange everything anyway. It is abrasion and tension and the slow work of materials aging. It is also, sometimes, an accident so mundane it feels insulting. A ship drags an anchor in the wrong place. A trawler pulls too hard, too long. A storm makes a vessel misjudge its position by a small amount, and a small amount is enough. And when a cable breaks, it is not a theatrical snap. It is often a quiet failure inside layers you cannot see. A kink that becomes a weak point. A pinch that crushes the delicate core. A split that lets seawater in. And seawater is patient. And seawater always wins eventually. You are close enough now to see that the cable is not perfectly clean. Silt has settled along its sides. Tiny ridges form where currents have nudged sand into little drifts. In places, the cable disappears under a dusting of sediment, then emerges again. It looks less like a piece of technology and more like a thing that has been accepted by the landscape. That is the odd comfort of it. Global communication depends on something you could touch. If you were reckless and wearing the wrong gloves, you could wrap your hand around it. It would feel cool and firm. It would feel boring. And that is the point. The modern world loves to pretend it is made of ideas, but it is made of metal and glass and scheduled maintenance. Now, follow the cable with your eyes and let it lead you like a trail. It runs straight, then dips gently, following the seafloor's slow curves. If you keep drifting, you start to notice something else. The cable is not alone. There are markers sometimes, and protective coverings, and occasional structures that look like small, quiet bumps. Those can be repeaters. They are spaced far apart, like lighthouses that nobody visits. Their job is simple. They take the light signals that have weakened, and they boost them again, not with magic, with power carried through the cable and careful electronics sealed away from seawater. A repeater is like a rest stop for photons, a place where the message gets a fresh cup of coffee and is pushed back onto the road. Even in the deep, physics insists on payment. Light traveling through glass loses a little energy as heat. It scatters, it fades, and if you want a message to cross an ocean, you must keep reminding it to stay loud. But tonight, one part of this long line is not doing its job. Somewhere ahead, there is damage. You cannot see it yet because the seafloor is wide and the darkness hides details until you are close. That is why humans do not send divers. Not here. Not at these depths, where the pressure is not a dramatic villain, but a constant fact. A human body is a bag of fluids and opinions. A robot is a patient machine, and it does not care about pressure the way you do. So the repair ship stays above, floating in the indifferent swell, like a hotel that never checks out. Inside that ship is a warm room, full of screens. There is coffee that has been reheated too many times. There are technicians who speak in calm voices, because panic does not steer well. And from that room, someone pilots an ROV, a remotely operated vehicle, an underwater work van with cameras for eyes, thrusters for muscles, and tool arms for hands. If you could see it approaching, it would look almost gentle. It has lights, but they are not harsh. They are practical. They cut cones through the black water, revealing dust and tiny drifting particles like slow snow. The ROV does not swim like a fish. It hovers. It nudges itself sideways. It corrects its position in small, thoughtful movements because the water pushes back. The pilot on the ship feels none of the water directly. They feel it through delays, through video compression, through sensor readouts. They steer with joysticks and controls that resemble a video game, if the video game was designed by people who hate fun. The screens show multiple camera angles, one wide view to keep orientation, one close view to see the cable, sometimes a camera on the arm itself, so the pilot can watch the tool approach like a slow-motion handshake. There is also sonar, a kind of underwater seeing, because light does not travel far here, but sound does better. Sonar paints the world in echoes. It tells you shapes, distances, and edges, even when silt makes the cameras useless. And silt is always ready to become uselessness. One careless thruster burst, and the seafloor blooms into a brown cloud. Visibility drops. The world becomes a smear of floating dust. So deliberate, hovering just high enough to avoid kicking up trouble. Its arms are not human arms. They have joints and grips and rotating wrists, but no skin and no nerves. They do not feel, they measure. They sense force through hydraulics and motors, through pressure changes and torque. The pilot learns to interpret that. A little resistance means the grip is too tight. A sudden drop means the tool slipped. It is not touch, not the way you understand touch. It is more like reading a mood from numbers. And yet, in good hands, it becomes graceful. One arm stabilizes, the other manipulates. The thrusters hold the whole body in place, fighting gentle currents, like someone trying to stand still on a moving bus. The cable lies below, and the ROV's lights wash over it. A small world forms inside the beams. Sand grains glitter. Tiny crustaceans flinch and settle again. The cable becomes a road, and the ROV becomes a maintenance worker, drifting down the shoulder. It is not hunting anything. It is not chasing a monster. It is not in a hurry. It is here for something almost boring, and that is why it works. Repairs in the deep sea are not dramatic. They are careful. They are repetitive. They are full of checklists and slow decisions. Now, before you can fix a cable, you have to find the exact problem. And that is harder than it sounds, because the ocean is very large and very good at hiding your mistakes. The first clue is often not visual. It is electrical, a change in signal, a sudden loss. Sometimes engineers can estimate where the problem is by timing. They send a pulse down the line and watch for reflections. This is called optical time domain reflectometry. In human terms, it is shouting down a hallway and listening for where the echo changes. If the light reflects back sooner than expected, something is wrong closer to shore. If it takes longer, the problem is farther out. It does not give you a perfect map, but it narrows the search. Then the ship sails to the region. It does not rush, because rushing at sea is how you invent new problems. Once on site, they lower the ROV, sometimes on a long tether, like a mechanical leash. That tether carries power and data. It is the umbilical cord that keeps the robot awake and obedient. As the ROV descends, it passes through layers of water that do not mix much. Temperature shifts, salinity shifts, currents shift. The robot does not care, but the pilot watches because each layer can tug the tether. Down near the bottom, the navigation becomes more precise. The team uses maps from earlier surveys. They use acoustic beacons, placed or already present, that let them triangulate position. They use the ship's dynamic positioning system, which is a fancy way of saying the ship tries very hard not to drift. Thrusters on the ship push against wind and current, keeping it hovering above the worksite. It is like holding a needle steady while sewing, except the needle is a ship and the fabric is the ocean. The search begins. The ROV flies slow patterns, like mowing a lawn in the dark. Its sonar scans. Its cameras stare. Sometimes it finds the cable quickly, a familiar line in the silt. Sometimes it takes longer because the cable has been buried or shifted or covered by a gentle avalanche of sediment. In places, the seafloor is smooth. In other places, it is rippled. There can be rocks and outcrops and small cliffs where the cable disappears behind a ledge. The pilot keeps the ROV low, but not too low. Low enough to see detail, high enough to stay clear of the sediment. Visibility can feel like driving in fog with your headlights on. The light reflects back from particles. Shapes appear late. Edges soften. The cable can look like a shadow until the angle is right. And sometimes the cable is not where the map says it should be, because the map was made years ago, because the planet does not hold still, because a landslide does not file paperwork. If you are lucky, the break leaves a visible sign, a section of cable lifted off the bottom, under tension, a kink, a frayed armor layer, a disturbed patch of sediment, like someone dragged a heavy rope across sand. If you are less lucky, the cable looks fine on the outside. The damage is inside, where the fiber has cracked, or water has intruded, or the signal is simply dead. Then you must use tools. Grapnels, cable trackers. Sometimes the ship will lower a grapnel to hook the cable and bring it up to test and inspect. But in many deep repairs, the ROV helps locate, confirm, and prepare the site. It is a slow conversation between machine and seafloor. Scan, pause, adjust, approach. The ROV's lights sweep over a stretch of cable, and you notice something subtle. A section that does not lie as smoothly. A slight bend that seems too sharp to be natural. The armor wires look disturbed, like hair brushed the wrong way. The pilot steadies the vehicle. The thrusters whisper. The arms hover nearby, not touching yet, because touching is how you stir silt, and silt is how you lose sight of everything. The camera zooms in. There, under the light, the cable's outer layer is scuffed. Not dramatic, just enough. A scrape that could have been caused by gear or rock or slow abrasion. But here is the thing about fiber optic cables. They do not need to look destroyed to stop working. A small bend, if tight enough, can cause light to leak out of the core. A micro crack can scatter the signal until it becomes noise. And noise is just information that has died and started to rot. The team confirms the location, the coordinates get logged, the ship adjusts position slightly above. The ROV holds station, hovering like a patient moth over a wire. Now the work changes. The searching stops. The craft begins. And once the break is finally resting in the robot's spotlight, the job becomes less like exploration and more like quiet underwater sewing. The first step is making the cable manageable. A cable on the seabed is heavy, but it is also stubborn. It wants to stay where it is. If it is under tension, it can spring in ways you do not expect. So the team works slowly, like handling a sleeping animal. Sometimes the ship will use grapnels to recover the cable ends to the surface. Often, the actual splicing of optical fibers happens on the ship in a controlled environment, because trying to align hair-thin glass strands perfectly in cold water with currents and silt is a cruel puzzle. So the deep-sea part of the job is frequently about retrieval and placement. The ROV helps clear the cable. It may use a water jet tool, a gentle stream that blows sediment away without digging a trench of chaos. It may use a manipulator to lift the cable slightly, testing how it moves. The arm closes around it with a careful grip, not crushing, not slipping, just enough to hold. The cable rises a little, and you see the underside, cleaner, paler, less coated in settled dust. It is like lifting a rug corner in an old room. Nothing scary, just proof that time accumulates quietly. If the damaged section is to be removed, the cable must be cut. Cutting a cable is not a violent act down here. It is methodical. There are specialized tools like hydraulic cutters that can slice through armor wires and layers. But the team chooses the cut points with care, because every cut means more cable to replace. And replacement is not free. So you measure twice and you cut once, because steel does not forgive impatience, because the cable is not just one thing. It is a stack of promises wrapped around a strand of glass that wants to be left alone. You watch the ROV bring the cutter closer, and the tool does not look sharp. It looks like a compact jaw, built to bite without drama. The pilot lines it up, and the arm holds steady, because wobble is expensive. The cutter closes, slow at first, then with a firm, hydraulic certainty. The outer armor gives way in stages, like snapping dry twigs, one by one. A few wire strands spring outward, not dangerous, just offended. Under that is a layer that feels almost ordinary, plastic and insulation, calm in the spotlight. And inside that, nested like a secret you did not ask for, is the working core. The fiber itself is fragile, and it is protected the way rich people protect jewelry. Layers of buffering gel sometimes. Strength members, sometimes aramid yarn, which is human for extremely tough synthetic thread. And somewhere in the center, the optical fibers, thin and glassy, waiting to be lined up again later. Down here, you are not doing the hair-thin alignment. You are just making clean ends and giving the ship something it can lift. That is the rhythm of deep cable repair. The ocean gets the messy part, and the ship gets the delicate part. The ROV may attach a line, a recovery rope, with a grip that will not slip. Sometimes it uses a soft strap, like a belt, wrapped around the cable without pinching, because pinching can become the next failure, and that would be embarrassing. You might expect sparks or bubbles or some cinematic nonsense, but nothing flares. The cable does not bleed. It just becomes two ends lying on the sand, suddenly less like a road. Now comes the part where tension matters. A cable on the seafloor is not always slack. It can be pulled gently by its own weight between slopes, like a clothesline sagging. It can be tugged by currents over years, a slow persuasion. So when you separate it, one end may creep millimeter by millimeter, trying to retreat. That is why the ROV holds it and why the ship is ready. You are watching a small, underwater choreography of restraint. The robot grips one end with a manipulator. The other arm places a clamp or a temporary holding device to keep the cable from wandering. Because wandering down here means getting buried, and being buried means you will dig later in a world that hates digging. The ROV clears sediment around the cut ends using a gentle water jet. Not a power washer fantasy, just enough flow to lift silt into slow motion clouds that drift away. The pilot keeps the thrusters polite. The vehicle hovers, stable as it can be, while the seafloor tries to make everything messy. Once the ends are secure, the ship can start recovery. Up above, a winch turns and a line tightens, and the cable begins its slow climb. You do not see the surface, but you can imagine it. A cold deck light, a technician in gloves, a section of cable emerging like a reluctant sea serpent, dripping and heavy. On the ship, the work becomes strangely domestic. Cables are laid into troughs and held in fixtures and treated like a patient on an operating table. The goal is to remove the damaged segment and replace it with a fresh length. That fresh length is called a spare, which sounds casual for something worth a small fortune. Inside the ship, there is a splicing room that feels almost rude. It is bright, it is warm, it smells faintly like plastic cleaning solvent and tired electronics. The cable is opened carefully, layer by layer, until the fibers are exposed, and now you are close enough to understand why they did not do this part underwater. Optical fiber is glass, but it is not like a window. It is a hair-thin rod, and if you breathe wrong on it, it complains. The splicer uses tools that look like tweezers designed by someone with anger issues. The protective coating on the fiber is stripped away, millimeters at a time. The glass is cleaned because dust is a villain at this scale. Then, the fiber is cleaved. That word means cut, but not like scissors. It means snapped with precision, so the end is flat enough to kiss another end. You are aiming for a surface so smooth that light will not scatter, because if light scatters, your signal turns into a whisper, and your whisper becomes a buffering wheel. Congratulations. Now comes fusion splicing. The ends are brought together in a small machine and lined up with cameras. Not one camera, several, because you cannot eyeball something that's small and pretend you are competent. Tiny motors adjust the fibers in fractions of a hair width, and then an electric arc flashes inside the splicer, a controlled spark. It melts the glass tips just enough to fuse them into one continuous path. It is welding, but for something thinner than a thread. After the arc, the splicer measures loss. Loss is how much light fails to make it through the joint. You want that number low because every joint is a little disappointment, even a perfect splice is not perfect. It is just good enough that the network will stop complaining. Then, the splice is protected. A heat shrink sleeve goes over it and a small reinforcing rod because the fused glass is still fragile. The cable is rebuilt in layers, sealing back the world you opened. Water-blocking compounds are added where needed because seawater is always auditioning. And once both ends are spliced into the replacement segment, the whole repaired length is tested. They send light down it and measure what comes back. They check continuity. They check attenuation, which is human for how much the signal fades with distance. They check the repeaters if the fault was near one, because sometimes the problem is not the cable. Sometimes a repeater fails. Repeaters are sealed pressure housings with electronics that must survive for decades. They are meant to be boring, and usually they are. But when one dies, it is like a street light going out in a tunnel. The rest of the system can reroute traffic for a while because the internet has redundancy like a paranoid organism. Traffic shifts to other cables. Network operators make quiet phone calls. Data takes longer paths, like commuters avoiding a closed bridge. Most people never notice until they do. When capacity is reduced enough, your world starts to feel sticky. Videos drop quality, calls lag. A website loads like it is traveling through honey, and down here, the ocean does not care. It keeps being heavy. It keeps being cold. It keeps pressing on the hull with the calm confidence of a planet. When the ship is satisfied with the tests, the repaired segment is ready to go back down. Now you reverse the earlier ritual. Instead of recovery, you pay out cable. A turntable, sometimes called a carousel, feeds the cable over rollers. It moves like a giant, slow tape dispenser. The repaired section is guided into the sea, and gravity does what gravity always does. It pulls, but it must not pull too hard. Cable laying has a constant anxiety called tension control. Too much tension and you stretch or damage the core. Too little and the cable can loop or kink, which is another kind of future failure. So, the ship monitors the line, and the ocean takes it back. The ROV waits below, lights on, watching the repaired length descend like a thick ribbon. It helps guide the cable into place because the seafloor is not perfectly flat. There are ridges and troughs and little dunes of sediment. There are rocks that can create abrasion points. So the ROV nudges the cable into a gentle route. Sometimes it places protective coverings, a split pipe, a mattress of articulated material, something designed to keep the cable from rubbing. Sometimes it helps bury the cable if the location is shallow enough or risky enough. Burying can be done by specialized plows pulled by ships. Down here, on deep plains, the cable often just rests on the surface. But near human activity, the seafloor becomes a construction site. A burial tool can use jets of water to fluidize sediment. That means it turns the sand briefly into something like soup. The cable sinks into it, and then the sediment settles again, covering the line like a slow closing eyelid. It is not glamorous. It is just hiding the vulnerable thing from sharp, curious machinery. Back at the repair site, the ROV lowers the cable with a final, careful motion. The manipulator releases, and the cable relaxes into the silt. It lies there like it always has. A dark line, slightly too straight, now whole again. If you could see the photons inside it, you would watch them return. Not as a beam, but as coded pulses, disciplined and indifferent. Your message is resume their commute through glass, through pressure, through cold. And no one down here applauds. The ocean does not clap. The fish do not care. The only celebration is the absence of alarms in a control room. The job is marked complete in logs with times and coordinates and part numbers. Because the deep sea loves paperwork, it just refuses to do it itself. And with the cable resting again, your attention starts to drift outward, because the deep sea is full of other quiet machines doing other gentle jobs in the same permanent night. Not every robot down here is a repair technician. Some are surveyors, slow and steady, gliding above the bottom like night janitors with graduate degrees. An autonomous underwater vehicle, an AUV, does not have a tether. It leaves the ship and it goes alone, following a pre-planned route. It navigates by inertia, by acoustic signals, by careful math that accounts for drift. It carries sonar that paints the seafloor in stripes, mapping texture and shape. Side-scan sonar sends sound out to the sides and listens for the echo patterns. It can reveal ripples, rocks, wrecks, and cables, all as shadows and sound. Multi-beam echo sounders look downward, creating detailed depth maps. The AUV cruises in straight lines, turns, comes back, turns again. It is mowing the lawn of the abyss, and it never complains about boredom. The data it collects becomes charts, and those charts become decisions. Where to lay a new cable, where to avoid unstable slopes, where the seabed is soft enough to bury or hard enough to abrade. Before a cable is ever placed, someone has already imagined it lying there, and that imagination is built from sonar and patience. Other robots are samplers. They do not fix things, they take things. A manipulator picks up a small scoop of mud. A corer pushes a tube into sediment and pulls out a layered column. That column is time, stacked in thin bands. Each layer is a season of particles drifting down. A little clay, a little shell fragment, a little volcanic ash. If the Earth had a day worth remembering. In those layers, scientists look for chemistry changes, for microfossils, for clues about currents and climate and oxygen. It is detective work, except the suspect is the whole planet. Some robots inspect pipelines, long metal lines that also cross the seabed. Pipelines carry oil and gas, and now increasingly other things, like carbon dioxide in some projects. Pipelines need inspection because metal rusts and joints can shift and the seafloor moves. An inspection ROV carries cameras and sonar, but also sensors. It might use magnetic flux leakage tools, human words for a way to detect corrosion by seeing how magnetism changes. It might use ultrasound to measure wall thickness, because you do not want to discover a weak spot by watching it fail. Failure down here is expensive, and it is also messy in a way that travels upward. Some robots visit shipwrecks, not as treasure hunters, but as librarians. They photograph hulls, beams, plates, and cargo holds. They build three-dimensional models from thousands of images. Photogrammetry is the method, and the result is a digital ghost you can measure. Wrecks change over time. They collapse. They become reefs. They leak substances that should have stayed sealed. And so, robots return year after year to see what time is doing. There are also robots that tend to scientific instruments left in the dark. Seafloor observatories sit quietly, listening. They record temperature, pressure, seismic vibrations, sometimes sound the low-frequency calls of whales, or the crackle of shrimp, or the distant groan of ice. These instruments can be connected by cables too, power and data lines running like roots. A robot may be sent to clean a sensor face, to replace a battery pack, to reconnect a plug. Underwater connectors are their own kind of nightmare. You cannot just stick metal into metal and hope. Seawater conducts electricity, and it carries salt that loves corrosion. So connectors are sealed, pressure-rated, and often oil-filled. Some use a design where two faces meet and squeeze out water, making a dry contact. It is like a handshake performed inside a wetsuit, in the dark, under pressure. The ROV's manipulator has to align it perfectly. If it does not, it can damage pins, bend housings, or trap grit that ruins the seal. So the robot approaches slowly, adjusts, backs away, tries again. You can feel the patience in the motion. This is maintenance culture underwater. Inspect, document, tighten, replace, leave it tidy. Not because the ocean deserves neatness, but because the next team will curse you if you do not. And the deep sea has a long memory, stored in logs and coordinates. Every job becomes a reference for the next job. A cable route recorded, a connector type noted, a seafloor hazard flagged. The work is not heroic, it is consistent. Even the ship itself is part of that culture. Dynamic positioning systems keep it steady over a site for days. That stability depends on thrusters and sensors and computers that constantly correct drift. The ship listens to wind and current like a tired animal listening for rain. It adjusts without making a big show. If the system fails, the ship can move, and the tether can swing, the tether can snag, or pull, or drag the ROV. So, redundancy exists here too. Backups for sensors, multiple reference points, procedures that assume something will go wrong eventually. Because the ocean is not malicious. It is simply reliable in its ability to complicate you. Speaking of reliability, you start to notice how predictable the deep sea floor can feel. Not lively, not colorful, just steady. And in that steadiness, life continues nearby, often unnoticed. It does not rush toward your lights like a movie monster. It drifts, it waits, it conserves energy like it is saving for a winter that never ends. A cable lying on the seabed becomes a small piece of structure in a mostly flat world. For some animals, that is enough to matter. You see a pale crab, legs thin and careful, moving along the edge of the cable. Not because it loves technology, because the cable makes a line, and lines can be shelter from current. A small fish hovers just off the sand, facing into the flow. It makes tiny adjustments, like a dancer practicing stillness. When the ROV's lights sweep past, the fish shifts away, unhurried. A jelly shape drifts through the beam, translucent and indifferent. It is mostly water, arranged into a decision to keep existing. Some deep-sea creatures are drawn to light out of simple curiosity, or confusion, or because their world is usually dark and anything different is worth inspecting briefly. but the inspection is often cautious. A slow approach, then a turn, then a fade back into black. The darkness takes them back gently, like a curtain closing. Deep sea life is built around scarcity. Food is not abundant down here. Most of it arrives as marine snow, tiny particles of dead plankton, fecal pellets, bits of tissue, dust from the surface world. It falls slowly, constantly, like a sad, nutritious weather. So animals save energy. They move less. They grow slowly. They often have soft bodies because building muscle is expensive. Some have enormous mouths relative to their bodies because when food appears, you do not argue. Others have bioluminescence, small chemical lights used for luring, signaling, or confusing. Bioluminescence is efficient, cold light. It is produced by molecules like luciferin and enzymes like luciferase. Human words for? A chemical reaction that turns energy into photons without much heat. You can think of it as nature's tiny battery-powered lamp. The ROVs, floodlights, are crude by comparison, bright, broad, and wasteful, blasting the scene like a parking lot at midnight. And still, life persists near your worksite. A worm tube protrudes from sediment, a small chimney made from mucus and grains. A brittle star sprawls across the sand, arms extended like a slow net. It is not hunting actively. It is waiting for something edible to touch it. Eventually, even bacteria are busy here, though you cannot see them. They coat surfaces in thin films. They feed on chemical gradients. They turn minerals and organic matter into energy with quiet efficiency. If a cable has been down long enough, its surface becomes part of an ecosystem. Not a lush one, but a functional one. A place to cling, a place to hide, a place to pause. And yet, for all this calm, the deep is not a stable museum. It has disasters too, quiet ones, the kind that happen without sound, the kind that leave the map wrong, the kind that pull cables out of place like someone tugging a thread, because the seafloor is not a floor, it is a skin stretched over a restless planet. And sometimes that skin slips. It happens on slopes, along continental margins, near submarine canyons. A little disturbance starts it. An earthquake tremor, a storm surge that loads sediment at the shelf edge, a buildup of material that finally exceeds friction. Then, a submarine landslide begins. It is an avalanche, but underwater, so it can travel far. The sediment can become a fast-moving, dense flow called a turbidity current. In that kind of flow, sand stops behaving like sand and starts behaving like wet concrete with ambition. It hugs the bottom, dense and forward, sliding through canyons like it remembers the way. You do not hear it coming because water does not transmit that kind of drama to ears. You just see the aftermath, later, as if someone rearranged the furniture while you blinked. A turbidity current can run for miles and miles, and it does not need permission. It can be triggered by something tiny, a little shake, a little slump, a little nudge. Then it becomes a long, underwater stampede of grains. Anything resting on the seafloor becomes part of its path, including your precious cable. You imagine the cable as heavy, armored, and confident, But the cable is only confident when the ground is confident. When sediment starts moving, the cable becomes a rope in a river. It can be dragged, lifted, buried, or snapped by tension it never asked for. The ocean does not target it. The ocean just does not care where you put your stuff. There is an old famous lesson here, written in steel and silt. In the early 20th century, telephone cables kept failing in the same region. Engineers noticed a pattern of breaks marching down slope, one after another, not random, not scattered, like dominoes, but underwater, and much more expensive. That pattern helped reveal what a turbidity current could do. A fast-moving sediment flow can break a cable, keep moving, then break the next one. It turns infrastructure into a measuring tape for disaster speed. Congratulations, your global communications network became a scientific instrument. Down on the bottom, though, the lesson is simpler. The seafloor is not a quiet carpet. It is a slow machine, and sometimes it slips a gear. Earthquakes are another gear slip, and they arrive without a countdown. Up on land, you might feel a tremor as a gentle wobble. Down here, a tremor can become a slope, deciding it is tired of holding itself up. The ground can crack, settle, heave, and slide. Cables stretched across uneven terrain can be pulled like guitar strings. Not enough to sing, enough to fail. Even when nothing dramatic happens, the bottom still changes. Sediment falls constantly, the patient snowfall of the ocean. Dead plankton, mineral dust, tiny shell fragments, and the odd crumb of surface life. It settles on everything, the way dust settles on unused shelves. Given enough years, even a cable can disappear under a thin blanket. Not buried deep, just softened into the landscape. That sounds protective, and sometimes it is. But sediment can also create problems. It can hide obstacles. It can bury joints in ways that make future repairs harder. It can shift, exposing a cable to abrasion again. The planet is always editing its own floor plan, and the repair crews, with their robots and logs, are always reading the newest draft. When a cable route is planned, people try to avoid steep slopes and unstable canyons. They look for plains, for gentle contours, for boring geography. Boring is good. Boring means the ground is less likely to suddenly migrate. But there is no perfect route across a living planet. Tectonic plates move whether or not you have meetings scheduled. Mud accumulates whether or not you have budgets. And so, maintenance becomes a kind of acceptance. You cannot freeze the seafloor. You can only keep returning with patient machines to put things back the way you want them. Sometimes the damage is not even a full break. Sometimes it is a partial failure. A cable that still works, but worse, more signal loss, more errors corrected by equipment at the ends, more quiet strain on the system. Because digital communication is not just light in glass, it is light with rules. The data is packaged, checked, and corrected. When errors rise, systems work harder to clean up the mess. That costs capacity. It costs latency. It turns a smooth experience into one with tiny stutters. And the ocean, again, does not clap or boo. It just keeps pressing down with several tons of weight on every small square of you. When a landslide buries a cable, the repair can become archaeology. You cannot just look and grab. You have to find the line under the blanket, That means sonar. It means cable trackers that can detect a signal or a metallic presence. It means careful digging, and digging underwater is mostly just convincing sediment to stop being where it is. Some tools use water jets to loosen the seafloor. Some use suction, like an underwater vacuum cleaner, with a very serious job. You move slowly because too much disturbance makes a cloud, and a cloud makes you blind. Blindness in the deep is not scary. It is just inconvenient, which is worse. Convenient things get done. Inconvenient things get delayed and logged and argued about on headsets. If the cable is deeply buried, sometimes the best choice is not to excavate at all. Sometimes you reroute around the problem. Lay a new section that bypasses the buried damage. The network is built with this kind of pragmatism, not romance. The romance is for marketing. The reality is for people with spreadsheets and salt water in their boots. Even earthquakes that do not trigger landslides can still shift cable position. A cable that once lay slack can become taut. A gentle bend can become a tight curve, and tight curves are a quiet killer for optical fiber. The glass wants a smooth path. Bend it too hard, and light starts escaping like water through a cracked pipe. Engineers call it bending loss, and it is exactly what it sounds like. The message leaks out into the cable layers, and it is gone. Not dramatically gone, just missing enough that the receiver starts guessing. And guessing is how you get a loading spinner at 2 in the morning. So yes, the deep sea is calm most of the time, but it is calm the way an old building is calm right up until the plumbing fails. And the plumbing in this case is carrying the thoughts of billions of humans, which feels poetic until you remember most of those thoughts are receipts and opinions. Still, the system hums along, mostly because it is cared for, it is inspected, it is mapped, it is repaired, it is rebuilt, not all at once, not with heroism, but with a rhythm. Find the problem, lift it, cut it, splice it, lower it, log it, move on. And as you drift over this idea of slow disasters and slower fixes, your mind naturally starts to rise upward. Not physically, not yet. Conceptually, because every repair down here is connected to something above, a call that goes through, a map tile that loads, a weather model that updates, a ship route that avoids a storm by a few miles and a few hours. The deep sea work is invisible, but its effects are mundane and constant, which is exactly how infrastructure prefers to exist. You picture the repaired cable again, lying in the silt. It looks like nothing, and that is the point. The success of this system is that you rarely think about it. If you do think about it, it is usually because something went wrong. And the quiet truth is that things go wrong more often than you imagine. Cables fail regularly somewhere on the planet every year. Not because the design is bad, because the planet is large and humans are busy and metal gets tired. Most failures happen closer to shore, where people fish and anchor and drag. Deep ocean faults happen too, just less often. And when they do, the repairs take longer because distance and weather and logistics are part of the cost. A cable ship might be hundreds of miles away when the call comes in. It might be in port, loading spare cable like someone stocking a pantry. It might be finishing another repair because maintenance is a queue. not a single event, and the sea itself decides the schedule. A storm can delay operations for days, not because anyone is afraid, because you cannot safely deploy heavy gear in high seas without inventing accidents. Cable work is full of tension, literally and emotionally. The ship must hold position. The line must not snap. The gear must not tangle. The weather must cooperate just enough. So when you imagine a repair, imagine waiting. Imagine checks and rechecks. The deep sea does not reward haste. It rewards patience and redundancy and boring competence. Speaking of boring competence, consider the way the network routes around damage. Your data does not insist on one cable. It takes paths chosen by protocols, the quiet rules of the internet. Packets of information go from router to router, like mail sorted by machines. If one path is down, traffic shifts if capacity exists elsewhere. This is why many outages feel like sluggishness instead of silence. The internet rarely dies outright. It limps, it detours, it apologizes by buffering. And because there are multiple cables between many regions, failure becomes a partial inconvenience. Unless you live somewhere with only a few connections, then a single break can matter a lot. Islands, remote coasts, places far from major hubs. A cut cable can mean slow service or no service until repair. And repairs to remote places can take time because ships are not teleporters. They are floating factories that move at the speed of fuel and weather. If you want a comforting thought, it is this. Even in a world full of satellites and wireless signals, humans still trust glass in a hose on the seabed. Because physics likes it, optical fiber carries enormous amounts of data with low loss. It is fast, stable, and hard to beat. Satellites are useful, and they are getting better. But a satellite link has higher latency because space is big and signals must travel. Fiber stays closer to the surface of the planet, and it takes a straighter, shorter path. So for bulk data, for core connectivity, the seabed wins. Your bed is comfortable, and the seabed is not. But the seabed is where your comfort gets its updates. Now, let the scene widen. Imagine the cable leaving the deep plain and climbing slowly toward continental shelves. These shelves are shallower, busier, and more chaotic. More fishing, more anchors, more construction, more storms stirring the seabed into motion. Near shore, cables are often buried for protection. The burial depth varies depending on local hazards and regulations. In some areas, the seafloor is too rocky to bury easily. Then protection might mean armoring, or routing, or placing concrete mattresses. A concrete mattress is exactly what it sounds like. A heavy, flexible covering that sits over the cable. It is comfort, but for a cable, and it weighs enough to stay put. In other areas, the seabed is soft, and burial tools can slice a narrow trench. The cable drops in, and the trench closes behind it. From above, you would never know. From below, it becomes just another hidden line in the sediment. Cable landing stations on shore are another kind of quiet place. They look like ordinary buildings, sometimes with extra fences and warning signs. Inside, fibers are managed, split, routed, and connected to terrestrial networks. It is not romantic either. It is racks of equipment, cooling systems, power backups, and alarm panels. Because every undersea cable eventually becomes a room full of blinking lights. And those lights, tonight, are calmer because a robot did careful work in the dark. You can sense how everything is layered. Seafloor cable, shore station, land fiber routes, data centers, switches, routers. Then your device, warm in your hand, pretending the whole chain is effortless. It is not effortless. It is just well maintained, and maintenance has its own kind of poetry if you are willing to lower your standards. But there is another angle to this, one that feels almost personal. You, in your daily life, rarely think about failure modes. You think about apps and messages and streaming. Down here, everything is designed around what breaks, what corrodes, what snaps, what leaks, what drifts. Engineering in hostile environments is mostly the art of managing disappointment. Steel disappoints by rusting. Plastic disappoints by aging. Electronics disappoint by heating, by shorting, by water intrusion, by time. So the design becomes layered, cautious, and redundant. Water-blocking gels swell when exposed, trying to plug leaks. Armors resist bites from anchors and the grinding of rocks. Repeaters are sealed like little submarines, meant to last decades. And still, eventually, something needs attention. That attention arrives as a ship, a tether, and a robot with patient hands. And as you hold that thought, you realize the deep sea is not the only place where quiet machines do quiet jobs. But, for now, you stay with the ocean. Because there is still more of the seafloor's slow drama to notice. There are places where methane seeps from the ground, feeding communities of bacteria and worms. There are hydrothermal vents where hot water loaded with minerals pours out like a strange underwater factory. These are not cable routes usually, because vents are inconvenient and hot and chemically aggressive. But they remind you that the seafloor is alive. Geologically, it is not just a flat place to lay things. It is a boundary between rock and water, constantly exchanging heat and chemistry. Even far from vents, the crust releases heat slowly. Not enough to warm you, but enough to drive subtle circulation in sediments. Pore water moves through tiny spaces between grains, carrying dissolved chemicals. This matters for corrosion, for sediment stability, for biology. Everything down here is slow, but nothing is truly still. A cable is a visitor. A long visitor, yes, but still temporary compared to plate tectonics. Some parts of the seafloor are spreading centers where new crust forms. Other parts are subduction zones where crust sinks back into the mantle. You do not usually lay critical infrastructure across the most active seams if you can avoid it. But the planet has seams everywhere, and the safest route is often just the least unsafe one. In subduction regions, earthquakes can be frequent. They can generate tsunamis that matter at the surface. On the bottom, they can trigger sediment failure. And after such events, cables may need inspection, even if no failure is reported, because you do not wait for the customer complaint if you can see the building shaking. This is why survey work is constant. Ships tow sonar arrays. ROVs run pre-planned grids. ROVs investigate anomalies. The ocean is mapped and remapped because the map expires like milk. Speaking of mapping, there is a gentle irony in how the deep sea is seen. You cannot see it directly very well. Light fades, quickly absorbed and scattered, so you see with sound. Sound becomes your flashlight, your measuring tape, your sketch pencil. A ping goes out, a ping comes back, and you infer a world. It is like living in a room where you can only understand shapes by tapping a cane. And the better your processing, the sharper the inferred picture. Modern sonar can produce astonishing detail, but it is still an interpretation, a translation of echoes into images. So when a cable is lost under sediment, you do not just look harder. You change your way of seeing. You switch frequencies. You fly different passes. You let algorithms pick out straight lines from natural randomness. Because a cable is a human line, and nature rarely draws straight. Unless it is a fracture, which is also a line. And now you have confusion. So you cross-check. You confirm. You treat certainty as something you earn. Slowly. That mindset, slow certainty, is the real skill in deep work. Robots provide the hands and eyes. Humans provide the patience and the decision-making. Even the best pilots get tired. So, shifts rotate and notes are passed along. The ocean does not care if you need sleep, but your safety procedures do. Because a tired pilot can crash an ROV into the seafloor. And then you have two problems. One broken cable and one expensive robot lying there like a dropped tool. Recovery of a stuck ROV can take days. It can involve cutting the tether, grappling, improvising, and all of that is done while the ship tries to hold position in wind and current. So, the culture is careful. Slow is smooth. Smooth is fast. And fast is how you break things. In the deep sea, breaking things is not a lesson. It is a bill. Now, while you are thinking about bills, consider the cost of these cables. Not the abstract cost, but the physical reality. Thousands of miles of specialized manufacturing. Glass fibers produced in controlled facilities. Steel armor drawn and wrapped. Repeaters built and tested. Cable loaded onto ships in enormous spirals. Routes negotiated with governments and agencies. Permits, surveys, contracts. Then the actual laying, kilometer after kilometer, carefully controlled. A single new cable system can cost hundreds of millions, sometimes more. And then you bury parts, armor parts, protect parts. Because humans near shore are creative in their ability to ruin things. So when a repair happens, it is not just technical. It is economic triage. Fix the minimum needed. Restore service quickly. Avoid future failure where possible. And document everything. Because documentation is a kind of armor too. But the best part for your sleepy brain is that none of this needs you to do anything. It happens whether you appreciate it or not, which is, honestly, the best kind of service. Now, the seafloor drama begins to feel familiar. Slopes fail, sediment moves, quakes shift the ground, repairs follow, so your attention can begin drifting upward toward the larger web that these cables create. Not just one cable, but many, crossing oceans in multiple directions. A mesh of routes chosen for politics, economics, geography, and risk. Some regions have dense clusters of cables, like highways. Others have only a few, like lonely roads. If you could see them all at once, the oceans would look stitched. Not tightly stitched, but enough to remind you that humans are always trying to connect themselves, even when the connecting medium is a place humans cannot comfortably inhabit. That is the odd tenderness of it. You build a nervous system across a hostile environment, and then you forget it exists. And yet, there are people who do not forget. They are the ones who keep a map in their head of lines you never see. They know which routes are crowded, which routes are fragile, and which routes are political nightmares. They know that a cable is not just glass and steel, it is contracts and weather windows. They know that if one link goes quiet, traffic does not vanish. It just gets grumpy. They also know the difference between a clean failure and a messy one. A clean failure is a straight cut, a sudden stop, a loud alarm, and a clear location. A messy failure is a slow fade, a rising error rate, a whispering loss that migrates. And you, tonight, get to ride that whisper upward, from the seabed into the invisible web above. Your repaired cable is only one strand in a stitched ocean. Above you, on the surface, there are other ships, other storms, other people pretending nothing depends on the seabed. But the network planners do not pretend. They build like pessimists, because pessimists get fewer outages. Redundancy is the polite word. Paranoia is the honest one. You picture the world as routers and blinking lights. But it is also geography. Cables land where the shore allows a stable trench. They avoid places where anchors congregate like bored birds. They choose routes around undersea cliffs, around canyons, around areas that slide. Then they negotiate landings with governments, with regulators, with property owners. Because the ocean is indifferent, but coastlines are opinionated. Once a cable reaches shore, it does not become magical. It becomes a building. A landing station sits behind fences, often plain enough to ignore. Inside, it is air-conditioned seriousness. There are racks, power supplies, and batteries the size of furniture. There are diesel generators outside, because the grid also enjoys failing occasionally. The cable comes in through ducts, and the fiber gets managed like hair in a salon. It is cleaned, spooled, labeled, and connected into terrestrial networks. If you are imagining a single strand of glass going straight to your phone, you are being optimistic. The signal passes through patch panels, optical amplifiers, switches, and routers. Each step is another chance for a tiny failure, politely prevented by more equipment. The fiber itself carries light, but the internet carries rules. And those rules are why your device can ask for something and actually receive it. Your request gets split into packets, small envelopes of data. Each packet is addressed, numbered, and sent on its way. Not all packets take the same path. Some take a longer route because a shorter one is busy. Some detour because a link is down. Some arrive out of order, like groceries delivered by different strangers. Your device reassembles them anyway, because it has learned to expect disappointment. That reassembly is why streaming works at all, and it is also why streaming can suddenly stutter, even when nothing looks broken. Sometimes the stutter is not your home connection. Sometimes it is a distant router dealing with an update. Sometimes it is congestion, too many people wanting the same thing at once. The internet is not a single pipe. It is a negotiated truce between many networks. Those networks exchange traffic at places called peering points, human words for crowded intersections where companies agree to share lanes. A major city can have buildings that function like data crossroads. Inside, fiber trunks enter like highways, and switches move traffic like patient clerks. It is loud with fans, because electronics are little heaters with delusions. You can smell warm dust, plastic, and filtered air. Not romantic, but very alive in its own sterile way. From that kind of building, your undersea cable becomes one option among many. If one cable is repaired, capacity returns, like a road reopening. Latency drops a little, congestion eases a little, and most people never notice, which is the highest compliment infrastructure can receive. But you can notice if you want to be quietly haunted by it. A message you send tonight may cross an ocean in a fraction of a second, not because the ocean is easy, but because someone built a glass nerve through it. The light in the fiber travels fast, but not infinitely fast. In glass, it moves at about 2/3 the speed of light in vacuum. Still fast enough to feel like magic to a human brain. But delay adds up, and routing adds more. Every amplifier, every switch, every cue adds a small pause, and that pause is why distance still matters, even in a digital world. You can feel it in a video call. When someone laughs a beat too late, that beat is the planet insisting you are not in the same room. The repaired cable reduces some of that insisting. It shortens detours. It relieves the other routes that were carrying extra load. And now, somewhere, a network operations center gets quieter. Those centers are rooms where people watch maps and graphs at odd hours. They see traffic levels as flowing lines, like weather radar for data. They see alarms, warnings, and the occasional red indicator that ruins a shift. When a cable fails, they do not scream. They open tickets. They reroute traffic where they can. They call the cable owners and the repair coordinators. They estimate impact and they write careful updates. The language is always calm because panic is not actionable. A cable repair itself can take days or weeks, not hours. The ship has to travel. The weather has to cooperate. Permits may matter near shore, and the sea has to allow you to hold station without violence. So network operators treat outages like injuries. You stabilize first, you reroute blood flow, then you schedule surgery, and sometimes you live with reduced capacity until the surgeon arrives. Not glamorous, but functional. You might assume satellites could replace all of this if the ocean is such a nuisance, but satellites are not a free escape. They have limited capacity compared to fiber. They are expensive to launch and maintain, and for many uses, they add delay because the signal goes up and down through space. Even a low Earth orbit satellite is still far enough to feel in timing. Fiber is stubbornly good at moving huge amounts of data. It is quiet, efficient, and hard to beat for bulk traffic, which is why the seabed remains essential, even as the sky gets crowded with hardware. So, your repaired cable is a small but important part of a global habit. Humans keep building lines between places because we cannot stand silence. And then we complain when those lines need care. Congratulations, you invented a world that requires constant maintenance. Now, speaking of maintenance, There is another quiet layer above the seafloor repairs. It is the planning that happens before anything breaks. Cables are monitored constantly, not by cameras underwater, but by signals and measurements. Engineers watch optical power levels, error rates, and alarms from repeaters. They look for drift, slow changes that hint at trouble. A gradual rise in attenuation can mean a bend is worsening. It can mean water is creeping somewhere it should not. It can mean a component is aging, heating, becoming unreliable. The monitoring equipment can do tests that feel like tapping a wall to find a hollow spot. A pulse goes down the fiber and reflections come back. The reflection pattern changes at splices, connectors, and faults. So a skilled engineer can read a trace and say, this looks like a bad splice, this looks like a break, this looks like a bend, this looks like trouble near the landing station. It is all done with light, timing, and a little suspicion. Even in normal operation, cables are treated as systems that will fail someday. That is why there are spare parts, spare capacity, and spare routes. A cable ship carries spare cable, but also spare repeaters in some cases, spare joints, spare armor components, spare tools that only exist for this one job. Because if you need a part in the middle of an ocean, you cannot visit a hardware store. You bring your own civilization with you. This is why cable ships look like working vessels, not yachts. They have cranes, winches, and large circular tanks called carousels filled with cable. The cable sits in those tanks in careful spirals, like a sleeping snake with a union contract. The ship can pay out cables smoothly while controlling tension. It can also haul cable back, which is harder because the ocean has opinions about giving things back. The ship uses rollers and chutes to guide the cable over the stern. It is all designed to avoid sharp bends, because sharp bends are a quiet assassin. And while this is happening, the crew watches weather, because weather decides whether you work. If waves get too large, heavy gear becomes dangerous. A swinging cable can injure people. A sudden slack can cause tangles. A sudden tension spike can snap the line. So crews wait sometimes for long stretches. They do maintenance on the ship, check tools, review procedures. They live in a floating schedule, always adjustable. The ocean teaches flexibility, whether you want the lesson or not. From your safe room, this kind of waiting sounds dull, but dull is survival. Dull is fewer accidents. Dull is why the repairs eventually succeed. Now let your mind follow a packet of data using your repaired cable. You are a tiny burst of light injected into fiber. You are not glowing for beauty, you are coded for meaning. You bounce inside glass, trapped by refractive index, held like a rumor in a corridor. The fiber has a core and cladding, two kinds of glass with slightly different properties. That difference is what keeps you from escaping. You travel and travel and travel through darkness and pressure you will never feel. Along the way, you pass a repeater sealed in metal. Inside, you become an electrical signal briefly, amplified, then turned back into light. Or in newer systems, you stay optical and get boosted by optical amplifiers. Either way, you are refreshed, pushed onward. You are not a single beam. You are part of many wavelengths. Modern systems use dense wavelength division multiplexing, human words for many colors of light traveling together in the same fiber. Each wavelength carries its own stream of data, like many radio stations on one wire. That is how one cable can carry ridiculous amounts of information. Not infinite, just enough to make you overconfident. Those wavelengths have to be managed. They can interfere, distort, and accumulate noise over long distances, so the system uses careful modulation, error correction, and amplification strategies. It is a dance between physics and engineering, performed in silence. And when the dance falters, humans send a ship, and then a robot. So yes, the web above the water is invisible, but it is not imaginary. It is physical, layered, and constantly audited. It is also vulnerable in ways that feel unfair. A single anchor in the wrong place can ruin an entire region's connectivity. A fishing trawler can drag gear and slice through a line. Sometimes it is accidental, sometimes it is careless, and sometimes it is just bad luck. The cable does not care why. It just stops being continuous. Then the repair begins, again, with its slow choreography. That repetition is the real story of infrastructure, not invention, but upkeep. Now, while you are still thinking about this global web, you start to notice something quiet and unsettling. All of this effort exists to move human thought around, and the ocean does not know or care what thought is. The seafloor holds your cable like it holds everything, with indifferent gravity. It is not impressed by your memes. It is not moved by your love letters. It is not offended by your arguments. It simply lets photons pass through glass because the glass is insulated from it. That indifference is the cozy horror of it. Your world depends on systems built into environments that would kill you quickly, and you sleep anyway because the system is mostly competent. Speaking of competence, the deep sea has another quiet workforce. Not the cable robots, but the robots that keep track of the ocean itself. Because cables are not the only reason humans care about the seabed. There are also currents, storms, climate, and the slow shifting of chemistry. Instruments sit on the bottom for years, watching. Some are connected by cables, some use acoustic modems, some store data until recovery. They measure temperature, salinity, and pressure. They measure oxygen and carbon chemistry. They listen for earthquakes and for the low songs of whales. They watch sediment traps fill, grain by grain, with the planet's falling dust. And sometimes an ROV visits them like a caretaker checking an elderly relative. It cleans a sensor face, it swaps a module, it reconnects a plug, then it leaves, because lingering is not efficient. This is another kind of web above the water, not data for streaming, but data for understanding. And it also relies on cables and connectors that can fail, which means the same repair culture applies. Everything is logged, everything is planned, nothing is assumed permanent. Now, you might expect that the deep sea is too remote for interference beyond accidents. But cables have always been strategically important. They carry money, government communication, and the daily nervous system of economies. In the past, telegraph cables were cut during conflicts. It was a way to silence an opponent, quietly and effectively. Modern fiber cables are also vulnerable, though the network has more redundancy now. Still, cable routes are studied, protected, and sometimes kept discreet, not because secrecy is perfect, but because inconvenience is easy to cause. This is why landing stations are guarded, This is why route data is handled carefully. This is why repairs can involve coordination with coastal authorities. The ocean is indifferent, but humans are not. And humans like leverage. Even so, most cable breaks are mundane. Anchors, fishing, abrasion, landslides. The boring causes remain the dominant ones, which is almost comforting in a tired way. Your world is mostly threatened by ordinary behavior, scaled up by volume. Now, let your attention drift back down for a moment, not to the drama, but to the quiet after. The repaired cable lies still, and the ROV has begun to leave. Its lights pull away, and the seafloor returns to being a plane. The cable becomes just another line, a slight ridge in silt. A crab pauses near it, then continues, because life does not schedule around your infrastructure. In the distance, the water is full of particles, marine snow, continuing its slow fall. This is what the deep looks like most of the time. Not adventure, but persistence. And above, the web keeps humming, mostly unnoticed. But there is something else worth noticing. While you are here, the ocean is not only a place where cables lie, it is also a place where robots have taught humans new kinds of patience. Underwater work has forced engineering to become careful, modular, and procedural, because improvisation is harder when you are operating through a camera feed and a tether. A manipulator arm cannot do what a human hand can do. Not yet. So tasks are designed to be doable with slow grips and predictable motions. Connectors are designed to guide themselves into alignment. Handles are designed to be grabbed by jaws. Fasteners are designed to be turned by tools with limited dexterity. This is a subtle kind of coevolution. Humans build machines, then change the world to suit the machines. The deep sea becomes a workshop built for robots. And once you see that, you start noticing it elsewhere. Factories on land are designed around robotic arms. Warehouses are designed around autonomous carts. Even your everyday devices assume a network that can recover from partial failure. The world is becoming more machine maintainable because machines are the ones who can stay awake. Now, speaking of staying awake, consider the pilots again. They sit in a control room on a ship, watching screens for hours. The ROV moves in slow precision. The pilot's hands rest on joysticks, making tiny corrections. The pilot is not in danger the way a diver would be, but the pilot still feels a kind of strain. If you make a mistake, the mistake is expensive. If you stir up silt, you waste time. If you snag the tether, you might lose the vehicle. So the pilot becomes calm by necessity. Calm becomes a professional tool. The voice over the intercom stays steady. The checklist gets read. The actions remain unhurried. This is one of the few places where slow is not a flaw. Slow is the correct speed. The deep sea demands it. Now, the web above the water continues to spread. New cables are planned constantly because demand keeps rising. Video streaming, cloud computing, remote work, constant synchronization. The planet's data appetite is not subtle. So, companies lay more fiber across oceans, upgrade repeaters, add more wavelengths. They also retire older cables sometimes because capacity and reliability improve. Some cables are left in place, inert lines on the seabed. Others are recovered in parts. Though recovery is not always economical, an abandoned cable becomes structure like any other object on the seafloor. It collects sediment, biofilm, and the occasional curious creature. It becomes part of the deep's inventory of human leftovers. Not trash exactly, but not exactly natural either. The deep sea is patient with leftovers. It does not decay things quickly because it is cold and low in oxygen in many regions. So objects can persist for a long time. A cable can outlast the company that laid it. It can outlast the technology standards that first used it. It can sit there quietly irrelevant while new cables carry the modern world above it. That is another kind of cozy horror. The seabed is a museum where the exhibits are mostly forgotten infrastructure. Now, let your mind return again to the idea of signals as light, because it is strange when you think about it gently. Your words, your images, your bank transfers are photons being guided like cattle. They are herded through glass by refractive boundaries, kept on track by repeaters. The photons do not know what they mean. They just move. Meaning exists only at the ends, where humans interpret patterns. In the middle, it is just physics, doing what physics does. That means the internet is not intelligent. It is obedient. It is a huge, layered set of rules for moving symbols. And yet, humans treat it like a place. They say they are going online, as if it is a room. But the room is actually a mesh of cable routes, radio links, routers, and power supplies. It is as physical as any road system, just harder to picture. And you are picturing it now, whether you wanted to or not. And if you follow that physicality for long enough, you end up thinking about failure in a different way. You stop asking whether the internet is real. You start asking which parts of reality are most likely to snap first. You imagine the cable as a line, but the line has choke points. It has narrow straits, crowded shelves, and coastlines full of sharp tools. If you want a gentle horror, picture a map where many routes squeeze through the same doorway. Because geography is a quiet tyrant, and it forces traffic through certain places. A narrow sea between continents, a shallow shelf where cables must land, a busy shipping lane where anchors go to misbehave. In those places, the network is not just engineering, it is diplomacy, permitting, and a constant argument with chance. And when chance wins, the response is still the same. A ticket opens in a network center. A ship gets tasked. A robot gets lowered like a calm hand reaching into a dark drawer. The part you do not see is the waiting that happens in between. The ship does not teleport. The spare cable does not appear from the ether. Weather does not care about your service level agreement. So the invisible web above water is always paired with an invisible calendar. A schedule of inspection runs. A schedule of ships repositioning between regions. A schedule of parts being manufactured months ahead. The system is modern, and it is also oddly old-fashioned. It depends on warehouses. It depends on ships. It depends on people rotating shifts and eating bad food at sea. Now, while you are still in this mood of quiet logistics, let your attention drift back down again. Not to the cable itself, but to the place where the cable rests. Because the seabed is not one uniform thing. It changes personality with depth, latitude, and geology. Some places are soft, fine mud, the kind that puffs if you look at it wrong. Some places are coarse sand heavier grains that settle quickly. Some places are gravel and rock, sharp and unforgiving, built for abrasion. And your cable has to live on whatever it gets. If it lies on mud, it may slowly sink until it finds a stable cradle. If it lies on sand, it may get undercut by currents that carve little troughs. If it lies on rock, it may rub in storms and tides until armor wires tire. So a good route survey is not just about where the cable goes. It is about what the cable has to endure while it goes there. This is why the robots that map the seafloor feel like part of the same family as the repair robots. They are all answering the same question in different ways. What is down here, and how badly will it try to ruin our plans? When an autonomous underwater vehicle runs a survey, you are inside a routine. You glide a few meters above the bottom, steady, sleepy, methodical. Your sonar pings outward, and the return echoes feel like fingertips reading Braille. Every rock becomes a bright mark. Every ripple becomes a repeating shadow. A cable can show up as a straight dark line or a thin raised ridge, depending on angle. A shipwreck becomes a dense cluster of reflections, like a pile of furniture in a hallway. And the vehicle does this for hours, sometimes days, following a grid that looks boring on paper. Boring on paper is exactly what you want, because boring means you are not improvising in a place that punishes improvisation. When the vehicle returns, the data is downloaded like a long dream being told to someone awake. The maps get stitched together, noise is filtered out, and eventually, someone sees a clean corridor on the seafloor and says, "Yes, put the cable there." That decision can save years of trouble, or it can just reduce trouble from frequent to merely inevitable. Now, if you keep looking at the seabed like this, you start noticing the slow neighbors of cables again, not the fish that drift through light beams. The smaller neighbors, the ones that do not leave when the spotlight passes. Bacteria form biofilms on almost any surface you give them. A biofilm is a slimy community, a cooperative smear of microbes and secreted gel. It is not elegant, but it works. It protects the microbes from the environment, and it helps them share resources. If you leave steel in seawater long enough, microbes can even influence corrosion. That process has a name: microbiologically influenced corrosion. Human words for tiny organisms helping metal fall apart faster. They do it by changing local chemistry, creating little pockets of acidity, or altering oxygen levels. The cable armor is designed for seawater, but seawater is not a single opponent. It is salt, pressure, and temperature. It is also biology, quietly colonizing surfaces like it owns the place. And biology usually does. Eventually, even the word corrosion feels gentle, like a slow apology. But corrosion is aggressive at the scale of decades. It is electrons being stolen. It is metal turning back into mineral because that is what it wanted to be in the first place. Engineering is the art of delaying that desire. You coat, you wrap, you isolate, you design drain paths. You use sacrificial anodes sometimes. A sacrificial anode is a chunk of metal that volunteers to corrode first. It is a decoy, installed so the important structure stays intact. Congratulations, even metal has to choose a martyr. Now, all of this makes the cable sound fragile, which is unfair. Most undersea cable systems run for decades. They survive storms, quakes, currents, and the daily indifference of seawater. They do it because engineers assume the ocean will cheat. So they build layers, and they build monitoring, and they build procedures. They also build recovery plans that are almost comforting in their repetitiveness. When a fault is detected, you isolate, you reroute, you test, you estimate location, you dispatch, you retrieve, you splice, you redeploy. It is a ritual performed by different crews in different oceans with the same calm motions. And rituals are soothing even when the ritual involves cutting $1 million hose. Now, let your mind drift to another quiet tool in this world. The grapnel. A grapnel is a simple idea that becomes complicated underwater. It is, in basic terms, a hook dragged along the seabed to catch a cable. But the seabed is not a clean floor. It is uneven, sometimes rocky, sometimes muddy, often full of things that can snag. So grapnels come in designs that match the job. A flatfish grapnel skims softly over sediment, trying not to bite too deep. A chain grapnel can bite into rough terrain and snag lines that hide in grooves. There are also grapnels meant to cut if you are intentionally separating a section. Dragging a hook in the dark sounds primitive, and it is, and it still works because the cable is long, and eventually the hook finds it. When it does, the ship feels a change in tension. Not a dramatic jerk, just a subtle heaviness that tells you something is caught. Then the winch hauls in slowly, because hauling too fast is how you turn a catch into a snap. You are always negotiating tension, always. Tension is the invisible villain of cable work. It hides in slopes. It hides in the cable's own weight, hanging in water. The cable is heavy, but it is buoyant too, because water supports some of it. So the weight you feel depends on depth, angle, and speed. Engineers model this with catenaries, the curve a hanging line makes under its own weight. Human words for the gentle sag of a cable between 2 points. That sag is not just geometry, it is stress distribution. And stress is future failure being born quietly. So when you recover a cable from deep water, you are lifting a long curve, not a straight rope. Part of it drags along the bottom. Part of it lifts into the water column. And at some point, the tension rises sharply as more of the cable leaves its resting place. This is why recovery is slow with constant monitoring, because the ocean does not allow you to feel with your hands. It forces you to feel through instruments. Load cells measure tension. Navigation systems estimate where the line contacts the bottom, and the crew listens not for sound, but for numbers drifting into dangerous ranges. If you do it right, the cable comes up like a long thought being pulled out of sleep, reluctant, heavy, dripping, and then finally resting on deck where it looks almost ordinary. And that is the strangest part. A thing that carries continents worth of conversation can still look like a hose. Now, if you keep hovering in this space between deep sea craftwork and global data flow, you start noticing the human compromises that make it possible, like the choice to do delicate splicing on the ship, or the choice to bury cables near shore, or the choice to route around hazards instead of fighting them. These choices are not just technical, they are about human limits, because you cannot send people down there for long. You can send a robot for hours, even days, but a human diver is constrained by pressure, gas mixtures, decompression schedules, and plain biology. At great depth, normal air is useless. Nitrogen becomes narcotic, a condition called nitrogen narcosis. Human words for your brain gets drunk on the wrong gas. Oxygen becomes toxic at high partial pressures. Human words for the thing you need to live starts damaging you. So, deep diving uses helium mixtures, careful monitoring, and expensive support. Saturation divers can live under pressure in chambers, breathing specialized gas for weeks. Then they decompress slowly, sometimes over days, to return safely. It is an extreme job, done by extreme professionals, and even they have limits. There is a depth where sending a person becomes more pride than sense. So you send machines instead, because machines do not get narcosis. They do not get tired in the same way. They do not need to come back up slowly, and they do not panic. They just break, which is easier to log. Now, there is a small trap here in how you imagine these robots. You might picture them as autonomous, thinking, adapting. Most work-class remotely operated vehicles are not that. They are obedient muscle with cameras. They do not decide. They are driven. The intelligence is mostly up on the ship, in a warm room, inside tired human minds. Some newer systems add autonomy, like station keeping or automatic heading hold. That means the robot can maintain position and orientation without constant manual correction. It is like giving the pilot a very patient assistant. But the actual delicate work still relies on a human choosing each move, because underwater environments are messy, and mess is hard for algorithms. A connector is not just a connector when silt covers the alignment marks. A handle is not just a handle when marine growth changes the shape. A cable is not just a cable when it is half buried and under tension. So, the pilot remains the decision maker, and the robot remains the body. This is why the control rooms on these ships feel like a specific kind of modern craft. Not blue collar, not white collar, but something in between. Screens and joysticks, yes, but also intuition and slow hands and a respect for physics and a quiet understanding that the ocean does not offer second chances quickly. If you drop a tool, it falls into a world that does not return things. If you damage a connector, you may be scheduling another repair. If you snap a cable end, you may be buying a longer replacement segment. Congratulations, your small mistake now has a budget line. Now, let your attention drift outward again, from the repair culture to the wider system, because there is a reason redundancy is treated like religion in networking. Undersea cables do not fail every day in one place, but they fail often somewhere, and when you add up all the somewheres, you get a steady background rate of trouble. So networks are designed to degrade gracefully. Graceful degradation is human, for things get worse without fully dying. Your video drops to a lower resolution. Your call gets a slight delay. Your file upload takes longer. It is annoying, and it is survivable, and it buys time for ships to move. But graceful degradation has limits. If multiple cables in a region are damaged, the remaining routes congest. Congestion is not a moral failing. It is geometry. Too many packets trying to share a limited lane. Routers begin queuing traffic like cars stacking at a toll booth. Latency rises because waiting is built into queues. Packet loss increases when buffers overflow. Then protocols kick in, resending lost packets, which adds more traffic, which can make congestion worse. It is a feedback loop that feels like the internet having a bad mood. Engineers manage this with traffic engineering. They shift flows. They adjust routing policies. They prioritize certain kinds of traffic because not all packets matter equally. A voice call hates delay. A file download hates loss less because it can retry. So the system makes choices quietly, without asking your opinion. And when the cable comes back online, the mood improves, the queues drain, the detours shorten. Everything becomes less sticky. You never see the repair ship, but you feel its effect as a calmer night on your devices. Now, since you are already thinking about moods and flows, it is worth noticing something else. Undersea cables are not evenly distributed because human population is not evenly distributed. Major hubs connect to major hubs. Coasts with big cities get more landings. Trading partners build direct routes. Tech companies invest in private cables to connect data centers. So the map of cables is also a map of power, money, and attention. Some regions have many redundant paths. Some regions have only a few. If you live in a well-connected place, you can treat outages as mild inconvenience. If you live in a place with one main link, an outage feels like isolation. Suddenly, distance matters again. And it matters for reasons that have nothing to do with your personal choices. Just geography, economics, and history doing what they do. Which is quietly deciding who gets reliable access to the shared nervous system. Now, bring your attention back to the seabed one more time, because the contrast is calming in a bleak way. Down there, none of these politics exist. A crab does not know what a peering agreement is. A worm does not care about cloud availability zones. The cable is just a ridge, a shadow, a convenient line to shelter beside. And the robot, when it appears, is just another visitor with lights. Some deep-sea animals are attracted to those lights, briefly. Not because they love technology, but because their sensory world is hungry for novelty. Light means maybe food. Light means maybe danger. So they approach cautiously, then retreat, conserving energy. Energy is the currency down there, and food is the rare paycheck. That scarcity is why deep-sea life often looks unfinished to surface eyes. Soft bodies, slow movements, pale colors, because color is expensive when nobody can see. And yet, there are also extreme specialists, creatures that turn chemical gradients into survival. At hydrothermal vents, bacteria use hydrogen sulfide as an energy source. That is chemosynthesis, human for making food without sunlight. Then, larger animals, like tube worms, build entire lives around those bacteria. The tube worms do not even have mouths in the usual sense. They host bacteria inside them, like internal gardens, and live on what the bacteria produce. It is efficient, strange, and very local. Vents are like small cities of life in an otherwise sparse landscape. Cable routes usually avoid them because vents are hot, corrosive, and geologically active, which is a polite way of saying they are a terrible place to put delicate infrastructure. Still, the existence of vents matters for the mood of the seafloor. It reminds you the planet is not just cold storage. It is a heat engine leaking through cracks, and the cables lie on top of that engine, pretending everything is stable. Sometimes stability holds for decades. Sometimes the seafloor edits itself quickly with a slide or a quake. Either way, the repair culture continues because humans are attached to continuity. We do not like gaps. We do not like silence. So we send machines into the deep to stitch the web back together. Now, speaking of stitching, notice how often the word splice appears in this story. Splice is an old word from rope work. It means joining two ends so they behave like one. It is a sailor word that survived into fiber optics, which feels appropriate because undersea cables are, in a literal way, modern rope. Rope carrying light instead of hauling cargo. The splice today is done with fusion arcs and microscopes, but the idea is the same. Continuity must be restored. Two ends must become one line again. And the ocean, as always, provides the setting where continuity is hard. Now, let your thoughts drift to the ship itself again, because it is a quiet character you only see indirectly. A cable ship is not just a platform. It is a tool. It has dynamic positioning to hover in place. Using thrusters controlled by computers, the system takes input from satellite navigation, gyro compasses, and wind sensors. It can also use acoustic reference beacons on the seafloor. For more precision, because satellite positioning tells you where the ship is on the surface. But the work happens deep below, and the tether can drift in currents. So the ship and the robot are constantly solving a geometry problem together. Where is the robot relative to the ship? Where is the cable relative to the robot? Where is the tension in the line? Every correction is small, but every correction matters. If the ship drifts, the tether can pull the robot sideways. If the robot gets pulled sideways, it can bump the bottom. If it bumps the bottom, it raises silt. If it raises silt, you lose visibility. If you lose visibility, you slow down. And slowing down is not a tragedy, but it is expensive. So the ship holds steady like a tired parent holding a stroller on a windy sidewalk. Now, the story you are in is still the same story. Patient machines, careful work, cold darkness. But the scale keeps changing, from fiber core to global network to seafloor geology. That is how infrastructure gets into your head. It is small and huge at the same time, a hair-thin glass strand